This begins section 2, the modeling of dynamic systems. In this section, we're going to be creating equations of motion using Lagrange's equations rather than Newton's laws like we did in system dynamics. We're going to focus in this unit on 1 degree of freedom systems, although this technique is going to be applicable also to 2-dimensional and multi-dimensional systems going forward. We're going to see how we can use Lagrange's equations to find the equivalent mass, the equivalent spring constant, and the equivalent damping coefficient in our systems. When we're dealing with systems that behave like springs, we're going to see how we can use the beam tables to find our equivalent spring constants. So how do we model our dynamic systems? First, we're going to need to select their objects and our degrees of freedom whose dynamics we wish to model. And as we saw in system dynamics, all the degrees of freedom are going to be perturbations measured from an equilibrium point. So when our system is at rest, there's no velocities or accelerations. That's going to mean that all of our degrees of freedom, whether they are linear measurements or rotational measurements, are going to measure 0. Then we start moving and we're seeing, are they to the right or the left, positive or negative, up or down, clockwise, counterclockwise from those equilibrium positions. Now in this step, when we're choosing degrees of freedom, it doesn't necessarily have to be all independent degrees of freedom. They might be interdependent, or if we know 1 degree of freedom, we can automatically always calculate the other. In this step, we want to make sure that we are kind of making our lives as easy as possible when we are going to start writing out the energies in the following steps. So the degrees of freedom we choose here are going to be mostly out of convenience to start the modeling process. Then we need to decide, how are we going to represent elements in our system? For this course, we're going to stick with simple or linear springs, masses, and dampers. So are objects in our system going to act like a spring? Is it actually a spring? Is there going to be friction in our system? Do we have to model that as a damper? Do we have things that simply dissipate energy? Are our masses going to be rotating and moving in a linear fashion, or maybe both? And we're going to see that some systems will be more simple, where there will be no damping that we have to account for. There'll be undamped systems, and some where energy is being dissipated. We're also going to see, are there external forces acting on our system, or is it autonomous, where we give it some initial conditions and then we let it go. Once we have the basics lined up, then we are going to choose a 1 independent degree of freedom for this unit. In the next unit, we'll have multiple independent degrees of freedom, and these are the degrees of freedom that we want to track as we solve the differential equation we're going to be creating. So we can start with multiple degrees of freedom, but eventually we need to narrow it down to just a specific independent degree of freedom, or degrees of freedom, that we're interested in solving for. Now, even if we start with multiple degrees of freedom that are interrelated, we're going to see that even when we narrow it down to, in this unit, a single independent degree of freedom, once we solve for that degree of freedom, we're going to be able to convert back to any of the other degrees of freedom that we're starting to work with, because we'll have some mathematical relationship that relates all the degrees of freedom to each other, at least in 1DOF systems. Now we're ready to actually start developing our equation of motion. We have our model, we have in our sights the degree of freedom that we want to be tracking. So we can derive our equation of motion, and we're going to be using Lagrange's equations in this course primarily. Again, this is in contrast to our approach in system dynamics. When we were talking about mechanical systems, we were using typically Newton's law. We were drawing a free body diagram, adding up all the forces, seeing what the accelerations were, and relating the two. We're going to see that Lagrange's equations is going to be an energy-based method for deriving our equation of motion, or equations of motion, whereas the Newton's law was going to be a force-based approach. But in the end, we're going to end up at the same place. We're going to get 1 equation of motion for our 1 degree of freedom systems, which is going to be a differential equation. So how do we get that general equation of motion when we are in 1 degree of freedom? So really what it's going to come down to is this differential equation is typically going to have an x double dot term, maybe an x dot term if it's damped, and an x term. So it's going to always look something in this form for the linear 1 degree of freedom systems that we are talking about. Now, we might have a fairly complicated system, even if it's only 1 degree of freedom. So usually when we're talking about the m, the c, the k in this equation, we're really talking about an equivalent mass, m, an equivalent damping coefficient, c, and an equivalent spring constant. So in a way, what we're going to be doing is adding up all the masses in our system, and that's going to be our equivalent mass, adding up all of our damping coefficients, adding up all of our spring constants. Now, we can't simply add them together, though, because of the different ways the degrees of freedom are going to relate to each other, and that's where our approach using Lagrange's equation is going to come into play in the upcoming slides. So we're going to be able to put it into this form. We could have a forcing on the right-hand side, or it could be a 0 on the right-hand side if it's autonomous, if there's no external forcing acting. But once we get into this form with our equivalent parameters, the m, the c, the k, then it's going to look like any second-order differential equation we've dealt with in the past. We're going to be able to find the natural frequency of the system. We're going to be able to find the damping ratio if it's damped. And eventually, we're going to be able to solve this system using the techniques we know from our ordinary differential equations class. And we'll be able to then find what is x of t. For these types of mechanical systems, we're going to be able to find what is the position of that degree of freedom at all times. Now, one note here, I'm using x here just generically as whatever the degree of freedom is we're trying to track. We're going to decide that before we get to this step, before we solve our differential equation, we're going to determine what is the degree of freedom that we want to be solving for, and then solve for that. So this is where we want to end up, is with this second-order differential equation. But the way we get there, again, is going to be different than how we did it in system dynamics, where we started with Newton's laws. Here we're going to be using Lagrange's equations, and this is a very general way to derive our equation or equations of motion that we're going to see in Unit 1 and Unit 2. So we're going to start with more specific, simple versions and then start to expand it out and see how it applies to more complicated situations. So right now, we're just going to be talking about conservative systems, so energy is not going to be dissipated, and they're going to be autonomous systems for right now. There's no external forcing. So what we're going to do is, looking at our system, we are going to find the energy contained in this system. We're going to see what is all the kinetic energy in our system, and we're going to create this variable we call T, which sums up all the kinetic energy in the system. And it's going to be time dependent, because as the system is moving, the energy might be converted from kinetic to potential back into kinetic. So the kinetic energy at any point of time is capital T. Then we looked at what is the total potential energy in our system, and we're going to call that V. And we're going to do this in terms of our selected independent degrees of freedom, which generically I'll just call x sub I. So again, we might start with a lot of degrees of freedom that are not independent of each other. We could derive our T and our V based on those degrees of freedom. Eventually, we will need to narrow it down to just the independent degrees of freedom that we are interested in. And using this T and this V, we are able to come up with this quantity called L, the Lagrangian. So L is defined as our kinetic energy minus our potential energy in our system. So L would also be a function of time. It can change. And this L we can use to derive our equation of motion. I'm not going to use that technique in this class, but there's other things we can do with the Lagrangian that are useful. So really this L I'm not going to use at all after this point, but just be aware that the Lagrangian is a quantity that we can calculate using our kinetic and our potential energy. But instead, the approach I'm going to take is using the T and the V directly to derive the equation of motion in the next steps. And this will go forward as we go into non-conservative systems and as we go into forced systems as well. So when we're dealing with these undamped systems, how do we come up with this equation of motion? So once again, we're going to first calculate the total kinetic energy, then the total potential energy in terms of our degrees of freedom. And we're going to see we have this general Lagrange equation for these systems. So we're actually going to take these quantities, the T and the V, and we are going to do partial differentiation on them. And we're going to see in a minute that out pops the equation of motion. Now, how do we go from the t and the v that we're calculating to the actual equation of motion is going to really be coming from a minimization of energy. We're differentiating these quantities with respect to our degrees of freedom or the time derivatives of our degrees of freedom. I won't go into the mathematical details of how we go from the t and the v to the end result. It involves variational calculus. We're not going to get into that. So you're just going to have to trust me for this course that we're going to be able to go from these energy quantities to an equation of motion. So if we see how we have the left-hand side set up here, I want to take the time derivative of the partial derivative of t with respect to our velocities. So this is the general equation. It's going to simplify down while we're in 1 degree of freedom, and when we go to multi-degree of freedom systems, we'll see how we can keep using this equation. We're going to add to that the partial derivative of our potential energy with respect to our position quantities. Again, in general, we could have multiple independent degrees of freedom, even though in this unit we'll only have one. So these xi's could be x1, x2, x3. We're going to see that we'll only have one for this unit. And in general, on the right-hand side, we could have a forcing, or we could have a forcing on each of our degrees of freedom as well, so we could have that f. So what comes out of this? Well, when we actually do this partial differentiation, we're going to see that this quantity, the time derivative of the partial derivative of t, well, we're going to get some quantity, some parameter times an x double dot term, or some second derivative term. That coefficient in front of the second derivative is what we are going to call the equivalent mass, and I'm denoting it here as MEQ. Then when we do the partial derivative of v with respect to our positions, we're going to get some coefficient in front of a non-derivative term, just x I'm going to call it here. That coefficient is going to be KEQ, the equivalent spring constant. Notice, again, we're just talking at the moment about undamped systems, so there is no x dot term. And then our right-hand side is unaffected. It's just going to be our forcing. And if we have an autonomous system, it's just going to be 0. For the most part, when after the point at which we are doing this differentiation, using our Lagrange equation to get our ordinary differential equation, the bottom term here, I'm typically going to not be writing the EQ after the M, the K, or the C. So in general, if it's just a little m, that is referring to the equivalent mass in our system. A little k is referring to the equivalent spring constant of our system. So some tips for how we get to our Lagrange equations and then eventually to our equation of motion. So it's going to be really helpful to draw schematic diagrams so that we can fully understand what are all the potential energies and kinetic energies in our system. A benefit of using Lagrange's equations, where we have this energy approach, is we don't need to draw a lot of free body diagrams, which are necessary for Newton's laws, because we need all the forces and all the individual accelerations. We can take a more whole systems approach when we're using Lagrange's equations, as long as we are accounting for all of the pieces of our system that have potential energies, kinetic energies, and then eventually dissipation when we're talking about damped systems. All right, so we are going to, up front, choose the independent degree of freedom or multiple independent degrees of freedom that we want to track. Again, just one for this unit. We'll write our t equation, we'll write our v equation. Maybe we'll start with more than just that one independent degree of freedom, but through some conversions, we have to get them each, the t and the v, in terms of just that one desired degree of freedom. Now we're going to start to see situations where the potential energies are more complicated than something that is just a simple spring in our system. We could have linear springs, we could have torsional springs. So those relationships we're going to understand. Those are going to be pretty simple. But we're going to start looking at systems where we have objects or bodies that act like springs. So if we're talking about beams that are deformable in some way, maybe an axial deformation, maybe a transverse deformation, really those beams are capable of storing energy like a spring does, and we're going to need to account for that if we have non-rigid bodies in our system. Other ways we get potential energy is if we have a mass that's changing its height. So the potential energy changes based on the height from the datum line that those masses are. Now, typically, for masses that change height, we do often ignore that because the potential energy is relatively small compared to the potential energy in our springs in our system. And also, it makes the math more difficult, as we'll see a little bit later. So typically, potential energy we have to look for are springs or objects that behave like springs. And then when we're looking at the kinetic energy in our system, we have to look at the two forms of kinetic energy we're going to have. Do we have an object with mass that is undergoing linear velocity? Because then we're going to have a 1/2 mv squared term as its kinetic energy. And do we have objects that are rotating, and they also have a mass moment of inertia? So in that case, we're going to have kinetic energy in the form of like a 1/2 I omega squared that we need to account for. And some objects might have both. They might be traveling linearly and they're rotating around some point, in which case we have to separately account for those things. So when we're forming the T, forming the V, we need to look at everything in the system that could have potential energy, add it all up together to get our V, all the things in the system that have kinetic energy, and add all of those up to get our T value. Then we can form the Lagrange equation, do our differentiation step, and we're going to get out our equation of motion.